Having trouble trusting a machine learning model, trying to understand what the model has learned from the data, wondering why the model gives the prediction. RuleMatrix is designed to solve these problems. It is a technique that helps you visually investigate the behavior of a given classifier. RuleMatrix uses rule induction techniques to extract a rule list that approximate the given model. Then, we use the rule list as an explanatory interface and present it using an interactive matrix-based visualization. So, how it works? Here is the pipeline for building up the rule-based explanatory interface. For a given machine learning model, we first extract the rule list from the model using a rule induction algorithm. The rule list serves as a simplified representation of the model. Then we use visualization to assist the understanding, navigation, and comparisons of the rules in the list. When the list is too long, we use rule filters and data filters to reduce the number of rules to show. Here, a rule list is an ordered list of decision rules. Each rule contains an antecedent and a consequent. The antecedent, that is, if, is a conjunction of multiple clauses. Thus, we only has and in the rule, and the rule will only fire when all the clauses in the rule are satisfied. The consequent, or the output of the rule, is a probability distribution of all possible classes. Since the rule list has an ordered structure, a rule will only be consulted when all its previous rules are not satisfied. The interface contains 4 components: the control panel, the rule matrix, the data filters, and the data table. The rule matrix consists of 3 parts: the data flow, the rule matrix, and the support view. In the rule matrix, each column represents an input feature. Each rule in the rule list is visualized as a row in the matrix. Each clause in a rule is visualized as a glyph in the corresponding cell. Multiple conjunctive clauses are visualized as multiple glyphs in a row. The range used in the clause is represented by a transparent gray box. The data distribution of the feature is also displayed as a histogram. This clause represents x larger than 19 and smaller than 36. The output of a rule is displayed as a colored number. The color encodes the predicted label of the rule. The number is the probability of the predicted label. The data flow shows the ordered structure of the rule list. The main vertical flow represents the data that remains unclassified. Each time the flow encounters a rule, a horizontal flow forks out, representing the part of data satisfying the rule. The support view visualizes detailed information about each single rule. The fidelity shows how reliable the rule represents the original model. The evidence shows the predictions of the original model on the real data. Striped boxes encode wrong predictions. We trained a neural network on the Pima Indian diabetes dataset. The model achieves an average accuracy of 72% on the test set. We use RuleMatrix to understand the behavior of the model. The first rule shows that if the patient has a high plasma glucose, the model would very likely to predict positive. This agrees to our knowledge in diabetes. The Rule 2 to Rule 5 show that the model would mostly give negative prediction. Go through these rules, we can conclude that the model thinks young patients with low body mass index is unlikely to have diabetes. We test these findings by using data filters. Now, the model almost predicts negative. Next, we studied the patients that have diabetes but are wrongly classified as healthy. We filter high glucose, which are very likely to have diabetes according to Rule 1, and those are unlikely to have diabetes. Then we find the model's performance on the filtered data dramatically drops to 56%. This means the model is very confusing at these patients. We oversampled this subset of training data and retrained the neural network. We found a significant growth of performance. Next, we present a case study of multi-class classification with the wine quality dataset. The wines have labels from 4 to 7, indicating the quality of the wine. We train the deep neural network with 6 layers on a wine quality dataset and extract a list of 53 rules from the neural network. Here we switch to divergent color and use a filter of 0.02. As we can see, RuleMatrix well handles the scalability issue and shows the important rules. Next, we want to see what the model regards as good wine. We click on the alcohol to highlight this column and find that good wines seems to have high alcohol. We adjust the data filter and find the resulting data are mostly colored blue, denoting good quality. Next, we want to see if there is any knowledge the model applies to differentiate level 6 and level 7. We find Rule 3 and Rule 7 have similar conditions but different consequent. Both of them use alcohol larger than 12 as a condition, but Rule 3 uses sulfates as another condition, while Rule 7 uses sulfur dioxide. These two rules shows that for wines with high alcohol, low sulfates and medium sulfur dioxide are more likely to be classified as normal good wine rather than pretty good wine.